wanted to start by just reviewing one more practice problem regarding balancing equations using redox. And so I'm going to do this one using the oxidation number method. So for permanganate, we have a +7. For the oxygen, for manganese, we had +7. For oxygen, we had -2. In the oxalate ion, the carbon is +3. And the oxygen is -2. For the manganese 4 oxide, +4 for the manganese, -2 for the oxygen, and then +4 for the carbon, and -2 for the oxygen and carbon dioxide. So these are our values. We can now look and setting it up. We've got our manganese pair, and in our manganese pair, we see that we are going from +7 to +4, which is a gain of 3 electrons. And in our carbon group, we see that we go from +3 to +4, which means we lost 1 electron. Now, I have made a fundamental mistake in my process so far. Can anyone tell me what my mistake is?
Your oxygens aren't balanced.
Okay, well, we're not worried about oxygen yet.
Okay.
We're still evaluating charges and electrons moving. There's something else that's missing that I haven't taken care of that I need to in order to do this step properly. Why is this 2 important on the carbon in the oxalate? No, why it's not charges. We've left something out. There are 2 carbon atoms in oxalate, each with a +3 charge. Yet in the product, I only show 1 carbon with a +4 charge.
You need to balance it.
Exactly. I need to balance my carbons before I can start doing this evaluation of charge business. So I need to go back and look at that. This is actually, I have 2 carbons going from +3 to +4, which means that it's a net of 2 electrons lost, not 1. Now, if I had carried this through the rest of the way, what I would have found is that I would have ended up multiplying this carbon reaction by 3. And when it came down to getting everything else balanced at the end, I would have run into a problem because my carbons wouldn't have been balanced. I would have had 6 carbons over here, 3 times 2. And I would only had 3 over here. And from a charge standpoint, everything else would have been kind of thrown off kilter as well, because this relationship is different, 3 to 2 versus 3 to 1. So what I need to do, now that I can see, okay, 2 electrons are being lost here, 3 electrons are being gained here, I need to use the lowest common multiple between 2 and 3 to get those electron numbers to eventually even out. And so the way to do that is to multiply my terms by the numbers to get me to that level. So to get to 6 electrons, I need to multiply this reaction by 3. To get to 6 electrons, I need to multiply this reaction by 2. And so my coefficients are going to change here. I'm going to go 2 on the manganeses. I'm going to go 3 on the carbons. And this 2 here is going to change. 2 times 3 is now a 6. So to satisfy the changes in electrons, I'm going to have to change my skeleton reaction as follows. And so just as a point of clarity here, we're going to rewrite our skeleton reaction using these new coefficients just so that we are on the same page. So there's my revised skeleton reaction. Now the next step, now that I've got my electron movement all set up, is to balance the overall charge. To balance the overall charge, again, I cut this in half and I evaluate. I've got 2 times the -1 charge for the permanganate and 3 times the -2 charge for the oxalate. -2 plus -6 is -8 as the total charge on the reactant side. And on the product side, I have 2 uncharged manganese dioxides and 6 uncharged carbon dioxides. Total charge on the product side is 0. Since we are in base, we are adding hydroxide ions. So we're going to add hydroxide ions to the side of the equation that is less negative. Which side of the equation is less negative, the products or the reactants?
You said is less negative?
Yes, more positive, less negative.
That'd be the product, wouldn't it?
It would be. I've got -8 over here on the reactant side. I've got 0 on the product or on the product side. So how many hydroxides would I need to add to that product side to get it to go from 0 to -8? How many hydroxides do I need to balance it?
If it's just a -1 charge, you would just need 8 of them.
Yep. So my product side is going to have 8 hydroxides in it. So I've added those 8 hydroxides to that side. Now in doing so, I've added a bunch of hydrogens here as well. I'm going to need to add waters to the opposite side to counterbalance that. Since I have 8 hydroxides that I added, how many waters am I going to need to add to the opposite side? Well, it's not going to be 0. I have 8 hydrogens on the product side now. I have 0 on the reactant side. So I've got 8 over here. I've got 0 over here. How many waters would I need to add? I need to get 8 hydrogens, so how many waters would that be?
4.
It'd be 4. Each water has 2 hydrogens, so 4 waters would give me 8 hydrogens in total. Okay, so now I put all of that together. Is everything exactly, Chasney? Exactly. So now I put all of that together in one final balanced equation: 2 permanganate plus 3 oxalate plus 4 water will make 2 manganese 4 oxides, 6 carbon dioxides, and 8 hydroxide ions. Now, as with any good chemical equation, we can always check and make sure that we've got everything. So if we wanted to do a quick check, we could look and say, okay, I've got 2 manganeses, 2 manganeses. I've got 6 carbons, 6 carbons. I've got 8 plus 12 is 20 plus 4, 24 oxygens. And I've got 4 and 12 is 16, and 8 more is 24, so oxygen's good. And I've got 8 hydrogens and 8 hydrogens. So atomically, I'm balanced. If I did this step up here correctly, I should be charge balanced, but just to be sure, -2 times -1 is -2. 3 times -2 is -6. -2 plus -6 is -8 on this side. And 8 times -1 is -8 on this side. So I'm atomically balanced. I'm charge balanced. I'm balanced. So that's really all that was necessary to balance this one. And again, this is using the redox, the oxidation number method. All right, any questions about this example?
No.
All right, so we're going to step away from this for the rest of this chapter, which is basically the rest of today. And we're going to start looking at concentrations in solution. And our concentrations in solution can come in a variety of different forms. So we're going to focus on a couple of different concentration calculations today. And when we look at chapter 11 starting next week, we'll focus on a couple of other ones. But the primary ones we're going to look at today have to deal mainly with mass and with moles. And so these are all ratio-based concentrations and solution concentration calculations. And so from that perspective, they're relatively easy to work with. Usually what we're dealing with is in the numerator some amount of solute, either in grams or in moles. And in the denominator, we're talking about either some amount of solvent, but more commonly here in chapter 8, we're going to be talking about some amount of solution. Again, either in grams or in some other cases, liters, where we measure out the solution in terms of its total volume, which is a heck of a lot easier than trying to measure out the number of moles in the solution. So, like I said, these ratios are quite common. What we're going to start with is we're going to look at mass percent. Now, mass percent we've already seen to some degree. We talked about percent by mass composition in chapter 2. We saw a touch of it in chapter 7. When we were doing empirical formula stuff, we saw mass percent there as well. Mass percent is real simple. It's the mass of whatever it is that we're looking at, usually the solute, divided by the total mass of the solution and multiplied by 100%. That empirical formula lab that you did, we had to use this mass percent to figure out the amount of copper in the product, which, based on the law of conservation of matter, was also the amount of copper in the reactant as well. And so using that value, we were able to kind of work backwards to figure out the empirical formula of the reacting substance. So this is mass percent. Now, what I want you to focus in on with regard to this equation is that this ratio is going to be used in other calculations as well. The mass of whatever it is we're interested in, usually the solvent, divided by the total mass. Now, what makes it a mass percent is the fact that we are taking that mass ratio and multiplying it by 100. As we will see in the next slide, that same ratio, mass of A, or whatever it is we're interested in, divided by total mass, can get copied and reapplied to other calculations. And so if I wanted to calculate parts per million, I would take that same mass ratio, and instead of multiplying by 100, which would have given me percent, I would multiply by 1 million to get parts per million. And in a similar fashion, if I wanted to do parts per billion, I would take that same ratio, and instead of multiplying it by 1 million or 100, I would multiply it by 1 billion. And so it's not often referred to this way, but percent means per 100. And so percentage can sometimes be referred to as parts per 100. It's rarely referred to that way. We usually refer to it as percentage, but the meaning is exactly the same, and the calculation is exactly the same, other than that multiplier that we stick on at the end. This multiplier ultimately tells us what the magnitude of the concentration really is. Because we would not use the same value for the same solutions. If I have a particularly concentrated solution, I'm not going to use parts per billion to describe it. The number is going to be gigantic. Same thing with parts per million. Where we find parts per million and parts per billion are when our concentrations are relatively small. So again, for those of you that are in the lab, think about the municipal water data. All of the data that I gave you for the municipal water was in parts per million. So what that means is, if something is 10 parts per million, then that means that there are 10 grams of that particular substance for every million grams of the whole sample of water. Another way of thinking about, another way of depicting parts per million has been milligrams of solute per kilogram of solution. We've seen that for parts per billion. We've often seen micrograms of solute per kilogram of solution. So there are lots of different ways of depicting these. But the main bottom line is that these are small amounts. These are small amounts. And so we really only see these values if we're dealing with really tiny concentration values. Now, so percentage-based, ratio-based values like parts per million, parts per billion, percentage are common, especially in health fields. You'll find concentration units such as those quite often in those areas. But in the laboratory, parts per million, parts per billion, percent by mass, not very common, not often seen. What we'll see more often, in fact, is molarity. Now, molarity is a ratio-based value as well. Molarity is the moles of solute divided by the liters of solution. And molarity has a lot of really key aspects for us that we like. First of all, molarity is something that is very easily comparable. Again, once we turn things into moles, that makes things a lot easier to compare in terms of their reacting power, in terms of the kinds of things that they are able to do. And so from a calculation standpoint, we often prefer molarity for those reasons. Not to mention, we've got, as a unit of measure, we've got volume. And so instead of having to run to the balance, measure out 50 grams of the solution, we can just go to a graduated cylinder or a burette or any kind of precise volumetric glassware and measure out the volume and know exactly how much solution solute, how much of our reacting material is in there. The other thing that we can do, because again, we're dealing with moles here, we can use this as a conversion factor in terms of determining how many grams of substance that we need, or as we'll see later on today, we can use molarity as a means for actually doing stoichiometry and calculating inside of a chemical equation how much stuff we're going to need. And the reason for this is, if we look at this as a ratio, remember, any fraction can be used as a conversion factor, because what that fraction states is that these two values are equivalent to each other. So if I tell you that you have a 3.01 molar NaCl solution, what that means is that there are 3.01 moles of NaCl per 1 liter of solution. And the sig figs in that value are in the numerator only, we can assume that the 1 here is an exact 1 by this definition. So the sig figs come in the number of moles that we say that we can generate out of that solution. Well, since this is a fractional value, we can manipulate, flip that fraction around any way we see fit to allow for whatever kind of conversions that we want. And so one of the most common conversions is if I wanted to figure out the number of moles in a sample of something, I could take the volume of that substance, multiply it by its molarity, and notice that in that scenario, my liters will cancel out, and that would give me moles. If I then took that number of moles, I could convert it to grams, just like we turn any moles into grams by using molar mass. If I multiplied that number by molar mass, moles would cancel out. I'd be left with grams left over, and that could tell me how many mole or how much mass of solute I ended up having in that solution. Or more often, we would use that kind of instant to figure out how to make the solution. So, you know, you're told, I want to make 100 milliliters of 5 molar solution. Well, you can use this kind of makeup, this dimensional analysis approach, to figure out how many grams of that solute that you need to weigh out to make your 100 milliliters of that solution. So let's do some practice problems here with relation to this kind of concept of solution making. So what is the molarity of an aqueous solution prepared by adding 36.5 grams of barium chloride to enough water to make 750 milliliters of solution? So out of this, we have to pull. I've got 36.5 grams of barium chloride, and I want to make 750.0 milliliters of solution. Okay. So the way that I can do this, I need to know, okay, I'm making molarity. So molarity is equal to moles of barium chloride, in this case, because that's my solute, divided by liters of solution. And so the first thing I need to figure out is the number of moles of barium chloride. The second thing I need to figure out is the number of liters of solution. And once I have both of those values, I can divide them into each other and get my molarity. So the first step would be, I've got my 36.5 grams of barium chloride. I need to convert that into moles. And so I'm gonna do one of my conversion steps here. I'm gonna need my periodic table. So barium is 137.33 grams per mole. Each chlorine is 35.45, and there are 2 of them. So 208.23 is my molar mass. 208.23 grams of barium chloride in 1 mole of barium chloride. And so to three significant figures, 36.5 divided by 208.23, I get 0.17, oops, 0.175 moles of barium chloride. So I've got the first part of the equation wrapped up. The second part, 750.0 milliliters of solution. Now, you don't have to do a conversion for this. If you are comfortable enough with the conversion between milliliters and liters to do this in your head, by all means, you can do so. But you'd end up with 0.7500 liters. And so the last step here would be to use the molarity equation. Molarity is equal to 0.175 moles of barium chloride divided by 0.7500 liters of solution. And to three significant figures, 0.175 divided by 0.75, I get 0.233 molar barium chloride solution. So molarity calculations and mass percent calculations, which we've already done to some degree, aren't too terribly difficult once you kind of know how to construct those ratios. Any questions about this problem?
No.
Okay, so these next couple of problems are going to be converting between units. And some of them are going to be a little bit easier than others would be. So here's a water quality question. The maximum concentration of vinyl chloride. Vinyl chloride is the precursor to PVC. The maximum concentration of vinyl chloride in drinking water is 0.002 milligrams per liter. What is that concentration in moles per liter? Okay, this one's relatively simple. We're going from 0.002 milligrams of vinyl chloride in 1 liter of solution. We're going to take that all the way to moles of vinyl chloride in 1 liter of solution. So my denominator is not changing at all. The only thing that's changing is my numerator. And so to that end, this isn't that terribly difficult of a problem. We just need to convert the milligrams of vinyl chloride into moles of vinyl chloride by some kind of means. Now, to help with that, it would help if we had the formula for vinyl chloride, and that is C2H3Cl. C2H3Cl is the formula for vinyl chloride. And so now we can set up our dimensional analysis. 0.002 milligrams of vinyl chloride in 1 liter of solution. And we're going to need 2 conversion steps to do this. First step, 1,000 milligrams in 1 gram. That gets rid of our milligrams. Second step, we need a molar mass. Molar mass of carbon, 12.01, and there are 2 of them. Molar mass of hydrogen, 1.01, and there are 3 of them. Molar mass of chlorine, 35.45, and there's just 1 of them. We get 62.50 grams of vinyl chloride. In 1 mole of vinyl chloride. And so our milligrams have canceled. Our grams of vinyl chloride have canceled. We're left with moles of vinyl chloride divided by liters of solution. And so if we do the calculation, 0.002 divided by 1,000 divided by 62.50, to 1 significant figure, because that's the only thing that we are given here, we would get 3 times 10 to the negative 8th molar vinyl chloride solution. And so we can see the value here, milligrams per liter. Again, that's another way of saying parts per million. And so the concentration there is 0.002 parts per million, which would be 2 parts per billion. And so at 2 parts per billion, we're talking at a concentration of 3 times 10 to the negative 8th molar. You can see from this why we tend to use parts per million and parts per billion to describe small concentrations as opposed to mass percent or molarity, because the numbers that get used are kind of too small to fathom. I can't really picture or understand what 3 times 10 to the 8th, 10 to the negative 8th molar looks like. I know it's small. I don't know. I just can't put my brain around how small that actually is. Whereas if I use parts per million or parts per billion, it says 2 parts per billion, I go, okay, 2 grams out of every billion grams, that's pretty low. So there is some backing and reasoning for why we have all of those different units for all of those different concentration values. All right, any questions on these first 2 example problems?
I don't have any.
All right. So let's try this one ourselves then. I'm going to turn this one over to you. You've got an aqueous solution of phosphate buffered saline, sometimes referred to as PBS. This is used in biological research as a way to wash and store living cells. So you put the cells in this solution, and it's isotonic, so the cells don't rupture, they don't die just because you've put them in an unfamiliar kind of territory. The ingredients in PBS include 10 millimolar sodium monohydrogen phosphate. What is the concentration of the sodium monohydrogen phosphate in parts per million? Now, just as a moment of clarity here, the relationship between molar and millimolar is the same as the relationship between any unit and its milli-unit. 1,000 millis fit into 1 molar. So keep that in mind as you're doing the calculation here. It's no different than any of the other metric conversions that we've dealt with in the past here. We're just attaching it to molarity as opposed to grams or liters or anything else. So what I want you to do, go ahead and try to do this calculation, do this conversion, come up with parts per million for it, and we'll see what it looks like on the other side. Now, again, just as a reminder, one of the alternative definitions for parts per million is milligrams of solute per kilogram of solution. Or milligrams of solute per liter of solution. So keep that in mind as you're doing the calculation and the conversion as well. So if you have questions, feel free to ask them. Otherwise, go ahead and just put your head down and work. And we'll come back in a couple of seconds and talk about it. Let's see how we did. So we are told that we have a 10.0 millimolar solution of sodium monohydrogen phosphate. And what we need to do is we need to convert that in and put that into parts per million. And so again, if we draw this out, if we kind of see where we are, we should be able to recognize that what we have is 10.0 millimoles of sodium monohydrogen phosphate in 1 liter of solution. So if I do some comparisons to my definitions of parts per million, I can see that this definition right here would seem to work really, really well. I already have my liters of solution, so I just need to turn my millimoles of substance into milligrams. Now, a number of different ways that we can do this. We could go through the process of turning our millimoles into moles. So 1,000 millimoles is going to be equal to 1 mole of the substance. And then one mole of the sodium monohydrogen phosphate is the molar mass, 141.96 grams of sodium monohydrogen phosphate. And then finally, we could turn that grams into milligrams. 1 gram is equal to 1,000 milligrams. And so when everything's all done canceling out, millimoles are gone, moles are gone, grams are gone. I'm going to end up with milligrams of sodium monohydrogen phosphate divided by liters. And so if I carry out the calculation, 10.0 times 141.96 divided by 1,000 multiplied by 1,000. So my thousands cancel out as well in this. I end up with 1,420 parts per million sodium monohydrogen phosphate. And so again, we see the reason why we don't tend to use parts per million for these kinds of concentrations that are relatively high. All right, any questions about this problem?
No.
No.
Okay, let's go ahead and take a break. It's 10:05 right now. Let's come back at 10:15. And we'll talk about dilutions, titrations, and we'll do one more conversion, which will show up on your chapter 8 quiz. And that's doing a conversion between mass percent and molarity. It's not a terribly difficult conversion to do, but it is something that you're going to need to be aware of because it will show up on the quiz. So 10 minutes, come back at 10:15. I'll see you then. All right, so before we fully came back and started looking at dilutions and titrations, I wanted to do a problem like this one here. Can everybody see the whiteboard?
Yeah.
Okay, so this kind of problem, I believe you have a homework question about it. I know you have a quiz question upcoming about it. It'll be on the quiz, which I think is Tuesday next week. And it's this: can you go between molarity and mass percent? And the answer there is yes, if you have a density. And so what I'm going to show you how to do here is how to use that density to help you to cross the bridge between these two units. And it's not all that difficult if you remember your definitions. So just to reiterate, 9.55% NaCl, what that would mean is that I have 9.55 grams of NaCl for every 100 grams of solution. That's what that percent is referring to in this problem. And then if I wanted to, I would get, and I could multiply it by 100% to get the percentage back. But really, that's what this means. Density. Density is equal to mass over volume. Now, what we have to remember about density is that the mass and the volume are of the same substance. And the substance in this case is the solution. So in terms of this particular problem, what we mean is that we have 1.06 grams of solution for every 1 milliliter of solution. Now, I make a big deal out of this because probably the most common mistake that students make is bending the density to fit whatever calculation or conversion is the easiest in their mind to do. So I've seen where density refers to grams of solute per milliliters of solution. I've seen where it's grams of solute per milliliter of solute. I've seen it done a number of different ways. And so I'm kind of giving you the warning here that there is a right way and a wrong way to interpret this. And if you go down the wrong way, you're going to run into problems. So here are my two scenarios. Here are my two ideas. Now, what I can see is that if I use this mass percent, the reality is all I need to do is two relatively simple conversions. I need to turn the grams of NaCl into moles of NaCl, and I need to turn the grams of solution into liters of solution to get it to molarity. So from that starting point, 9.55 grams of NaCl, my first step would be to convert that into moles. And so I've got grams of NaCl on the denominator, sodium 22.99, chlorine 35.45, 58.44 grams of NaCl in every 1 mole of NaCl. So that's my numerator. And in the denominator, I have 100 grams of solution. And here's where the density is going to come in. 1.06 grams of solution for every 1 milliliter of solution. And then one last conversion, turning those milliliters, 1,000 milliliters up, in fact, into 1 liter. And so if I do these two calculations, 9.55 divided by 58.44, I'm going to get 0.163415468 moles of NaCl. Now, the reason I haven't rounded this yet is because I want to avoid rounding errors. I want to avoid rounding errors. So I'm going to round this to 3 significant figures at the very end. In the denominator, 100 grams divided by 1.06 divided by 1,000, I get 0.094339622 liters of solution. And so if I carry that through then, I do all the calculations, I would get to 3 significant figures, since I started with 3 over here, 1.73 molar NaCl. So if you see a problem like this, or if you see the reverse of it, where you're given a molarity and you're asked to flip it around to do the opposite, to do percent, all that you have to do is break it down into its parts. You're going to have the solute as one component, the solution as a second component. You can convert each of them individually and then combine them together to get whatever value it is that you're trying to do. All right. Any questions with this one?
No.
All right, then let's move on in our discussions of solutions by looking at some dilutions. And so dilution is often something that we do, especially in our laboratory. Most things that come to us from chemical suppliers come to us in a concentrated version. That's to obviously save money, but also to save space as well. If you can have a stable solution that's concentrated, it's going to take up far less space for the same amount of reactive power than a larger series of diluted solutions. But the process of dilution is a rather simple one. All that we're doing is we're adding more solvent, which is usually water in these cases. We're adding more solvent to the solution that we have. And in the process, we're lowering its concentration because we've got the same amount of particles, but now it's in a larger space. And so we can see in this example here, let's imagine that we've got 5 particles per unit volume here in the dark green one. As we add water to it, we still have 5 particles, but notice now the 5 particles are getting spaced further and further and further and further apart. So the number of particles hasn't changed. What's changed is the space between them has changed and become more and more diffuse. And so there is some terminology that is associated with this. The terminology here, we can call a stock solution. A stock solution is basically any concentrated solution from which we will dilute. So if I am going to dilute a solution in particular, I'm going to take some amount of my stock solution, add some water to it, and that is going to be the diluted solution afterwards. A stock solution is different from a standard solution. In a standard solution, we know the concentration very, very well. Now, we might end up having to dilute that standardized solution along the way, but overall, the whole point of a standardized solution is that we know its concentration quite well. And so oftentimes what we'll do in laboratories is we'll take a stock solution, we'll dilute it down in some kind of a way, and then we'll do a series of processes to help us to standardize that solution so that we know its concentration quite well. But if we want to get a good idea of what a solution's concentration is, we can use a dilution equation to get us in the right idea. Keeping in mind that molarity times volume will always give us moles, if I know the molarity or the volume, I can kind of figure out what's missing just by doing this dilution equation. And the dilution equation is this: M1 times V1 is equal to M2 times V2. My initial molarity, and so we can kind of think of these as our stock solutions. My molarity of the stock times the volume of the stock that I use is equal to the molarity of the diluted solution times its volume. And so more often than not, what we'll see in problems of this kind is we'll look and say, okay, I know my initial concentration of my stock solution. I know what I'm trying to make. How do I make it? And so using this equation, you can kind of do it algebraically and solve and say, okay, this is where I'm going, and this is where I'm starting. This is how much of that stock solution I need. And that's probably the easiest way to do most of those kinds of problems. So let's take a look at an example. Hydrochloric acid. Most times when we encounter hydrochloric acid, it comes in the form of 12 molar stock solution. And that's generally how it comes from most chemical manufacturers. Now, in your lab kits, you're not going to be given no 12 molar HCl. I think you're given 1 molar if you have hydrochloric in yours at all. But for the most part, when a chemistry lab or a manufacturer or some kind of research facility gets hydrochloric acid, this is how it comes. And if you need a lower concentration, you have to make it yourself. And so the question here is, what volume of stock solution would be required to make 500 milliliters of 0.145 molar diluted solution? So the process here, we're going to use our titrate or our dilution equation. M1 times V1 is equal to M2 times V2. Our molarity of our stock solution is 12.0 molar. We're trying to figure out what the volume is that we need. So that's our V1. And we're going to a 0.145 molar solution that is 500.0 milliliters. Now, one of the really nice things about using this particular equation is that you do not have to change your units. So long as the units on the left-hand side of the equation match the units on the right-hand side of the equation, you do not have to go back and forth between milliliters and liters, liters and kilograms, or whatever it is. So long as the units are the same on both sides and they're both volumetric, they're both concentration units, we can leave it as it is. So this works for more than just molarity. If I have a solution that is 9% by mass, I can figure out what the diluted concentration will be in percent by mass. So long as the concentration units are the same, so long as the volume units are the same, we'll be okay. So algebraically speaking, we're going to isolate by dividing each side by 12.0 molar. My molarities will cancel out. So 0.145 molar times 500, 0.0 milliliters, divided by 12.0 molar to 3 significant figures. I'm going to get 6.04 milliliters of stock HCl solution. And so that's all that really is to this. When we're doing these kinds of dilution equation calculations, it's just a matter of solving the algebra and getting the algebra to work out for us and isolating the variable that's missing. Any questions about this example?
I don't have any.
All right, then let's move on and talk about titrations. Now, titrations are used in the laboratory. And this week you would have done a titration if you had lab kits. But you should be able to hopefully do one next week. In a titration, what we're talking about is this is an analytical method that we use to determine the concentration of a solute in a sample by reacting it with something that we know is concentration. So this is where those standardized solutions really come into play. Now, when we do a titration, what we are trying to find is the equivalence point. That is the exact point in the titration where the number of moles that we are titrating equal out with the number of moles of the other reactant. And so we hit that stoichiometric point where they're exactly even with each other, and we can use the fact that we know how many moles are in the one solution to figure out how many moles are in the other solution. That's the ideal. However, that's not always easy to do in practice. Because usually speaking, we are given no visual indicators as to when the equivalence point has been hit. To find it precisely, we usually have to use electronic techniques or pH-oriented techniques or graphical techniques or a combination of all three to actually find the true equivalence point. So what we do instead is we often rely on something called the endpoint. Now, the endpoint relies on something called an indicator. An indicator is just a chemical dye of some kind that changes color based upon pH changes that are occurring inside of the solution. And so when our indicator makes the appropriate color change, that's when we know to finish the titration and start running our calculations. Now, depending upon which indicator we use and what our titration looks like, our indicator can be pretty accurate in terms of getting us close to the equivalence point, or at least close enough to the equivalence point that we're really talking about differences of fractions of milliliters and fractions of error as a result. And so this is what indicators look like. And so the most common indicator used in chemistry lab, especially at this level, is phenolphthalein. Phenolphthalein is a really common indicator because it has a pH change that occurs somewhere between pH 8 and 10. And because of how quickly pH changes near the equivalence point, that actually can get us, if we do it correctly, around within 1/10 of a milliliter or so. And so phenolphthalein is popular. It's got a really definitive, distinct color change. We're going from a colorless solution in acid to a bright pink solution in base. And so you get good enough with the titration, you can see the difference pretty easily. And you can get relatively close, especially all things considered. Another common choice is something like methyl red or methyl orange. You see these not used so much in the types of titrations we would do in our lab, but in titrations where the equivalence point may be on the more acidic side, methyl red is a very common indicator for that because of when it changes colors. And there are others in there. There are a wide host. There is a large variety of dozens of indicators that are used for different purposes and different types of titrations. But what we're going to focus on as far as titrations and solutions and those kinds of things, we're going to look at something called solution stoichiometry. Now, in solution stoichiometry, what we are focusing on is the fact that, if you remember from chapter 7, we constructed this idea of a mole map that allowed us to go from moles of one substance to moles of another substance, provided we had a balanced chemical equation. Well, we can add to this mole map we can add to this mole map using some of our concepts that we've already talked about today. So if I take a solution if we approach it from this particular standpoint, where we've got a solution and using our concept of molarity, we can accurately convert between the volume of solution that we have for that particular substance and its number of moles, keeping in mind that molarity times volume equals moles, or if we rearrange that equation, moles divided by volume equals molarity. So with this little wrinkle in mind, we have another way of converting, and we can actually use this for a number of different kinds of conversions. So let's say that we wanted to use molarity to figure out the number of grams in a substance. Well, we talked about that already as a construct. This mole map would help us to deal with that. Molarity times volume would give us moles. Moles times molar mass would give us grams. This is the visual picture of what we talked about before the break. But if I wanted to go from volume of one solution to grams of another reactant or grams of product, I could do that as well. I would take the volume, use the molarity to convert it into moles, use the balance equation to convert the moles of the solution into moles of the other substance, and then I could use the molar mass to figure out the number of grams. So this is a wrinkle that we can add to our discussion of our mole map, of our organization of calculations that can really help us along the way here. Now, for titration, so if my starting point and my ending point happen to both be volumes of concentration. So if my pathway looks like this, there's actually a reduction of this that I can use. So instead of doing the full-on stoichiometry and doing all of the conversions and whatnot, there's actually an equation-based version that I can use where I modify that titration equation and I include one little extra piece. And that little extra piece is the part where we integrate that balanced chemical equation. These are the coefficients for the acid and the base in the balanced chemical equation. Now, what we'll find is that this works for any titration as well. It does not have to be an acid-base titration. It can be a redox titration as well. It can be any kind of titration that involves knowing the concentration of one substance and trying to convert it to the concentration of another substance. But this condenses down some of the calculation work that we have to do. So if we have a titration reaction, we can use this equation instead of doing the more complicated stoichiometry using the mole map. So let's do a couple of examples before we call it a week here. First question, what is the concentration of sulfuric acid if 15 milliliters of it reacts with 18.45 milliliters of 0.0973 molar NaOH solution? Now, when you get a problem like this, your first instinct is to just immediately bolt into the titration equation or the dilution equation and try to solve it that way. The problem with that line of thinking is that we don't have a balanced chemical equation yet. Before you do anything involving calculations in reactions, you need to know what the balanced equation is first. And so from that standpoint, we have sulfuric acid, H2SO4, reacting with sodium hydroxide, and the products of this neutralization would be water and a salt. If you didn't know that, if you didn't remember that, go back to the video where we talked about acid and base reactions. That's where this idea comes from. And the salt here would be sodium sulfate. And if you follow along with the balancing, I would need a 2 for the sodium hydroxide and a 2 for the water to get everything to balance out. And the reason why this is important is if you had just thrown this immediately into the equation, you would have had ones in those denominators, and this is not a one-to-one relationship. You'd have ended up coming up with an answer that was off by a factor of 2. So now that we have all of the information in front of us, now we can do the reaction. Molarity of the acid multiplied by its volume, 15.00 milliliters, divided by its coefficient, 1, is equal to the molarity of the base, 0.0973 molar, multiplied by its volume, 18.45 milliliters, divided by its coefficient, 2, so solving out the algebra here, the molarity of the acid is going to be equal to 0.0973 molar times 18.45 milliliters times 1 divided by 2 times 15.00 milliliters coming from the other side. Let's see, milliliters cancel out. Molarity is the only thing that's left over. And so to 3 significant figures, 0.0973 times 18.45 divided by 2 divided by 15. We would get, again, to 3 significant figures, 0.0598 molar sulfuric acid. If you had done this without doing the coefficients in the numerator, or excuse me, in the denominator, you would have ended up getting an answer that was twice as big. You would have ended up getting something around 0.118 or something along those lines. So it's important always to have a balanced chemical equation before we do anything else regarding calculations, especially in these titration kinds of problems. Right? Any questions?
No.
All right, let's do another example. All right, this one's a different one. This one is not a titration, so we're going to have to use solution-based stoichiometry. What mass of sodium hydroxide is needed to precipitate the cadmium-2 ions from 35 milliliters of 0.500 molar cadmium-2 nitrate solution? Okay, so there's some layers in here that are important. But nonetheless, if we go to our mole map, we would see that we are starting from a volume of cadmium 2 nitrate, and we would have to go from there to grams of sodium hydroxide. So our first step is going to involve molarity, converting volume into moles. Then we're going to use our balanced equation to go from moles of cadmium to moles of sodium hydroxide. And then we would use moles of sodium hydroxide to get us to the grams using the molar mass. So that's the direction that we're going to have to go. Let's see about how we use that. So we have 35.0 milliliters of cadmium 2 nitrate solution. Now again, what we're going to need is a balanced equation between the two. So before we get too far ahead of ourselves, we got to get that balanced equation in. Cadmium 2 nitrate plus sodium hydroxide is going to lead us to cadmium 2 hydroxide and sodium nitrate. So there's our equation. I went ahead and pre-balanced it for us. Again, this particular step was important because we would have not come up with the correct answer in terms of the relationship between these two without the balanced equation. Now that we have it, it's a matter of putting together the appropriate pieces to get us to where we need to go. So our first step is going to be to convert that milliliters into liters. Now that we have that, now we can use our molarity. 1 liter of solution is equal to 0.5 moles of cadmium nitrate. And so we have canceled out the milliliters. We've now canceled out the liters of solution. And we've got moles. 1 mole of cadmium nitrate is going to react with 2 moles of sodium hydroxide. And then since we're going to mass here, our last step is going to go from grams to moles. or moles to grams in this case, 1 mole of NaOH. Sodium is 22.99. Oxygen is 16. Hydrogen is 1.01. We get 40.00 even. As our mass of sodium hydroxide. And just to make sure everything cancels out, we've got our moles of cadmium nitrate, they cancel. Our moles of sodium hydroxide cancel. We're left with just grams of sodium hydroxide, which is a mass, which is what we're looking for. So putting it all together, 35.0 times 0.5 times 2 times 40 divided by 1,000. And I get to 3 significant figures, 1.40 grams of sodium hydroxide. Right? So when we have stoichiometry, when we have calculations involving reaction equations, which is the simplest definition of stoichiometry that there is, when we have that as a possibility, then all we have to do is treat it just like any other stoichiometry problem. And the only difference is that instead of using grams and moles, we're going to have to use molarity to get us out of that solution conundrum. Now, we will see other situations similar to this later on. When we talk about gases, we will use a different equation to get us between gas volume and moles of gas. But the scenario, the situation is essentially the same. If we are dealing with something that is not grams, not particles, we can use some kind of equation or conversion to get us 2 moles to allow us to do the normal kinds of calculations that we saw in chapter 7. Right? Any questions about this example?
No.
All right, last example, and then we'll call it a week. Go ahead and work on this yourselves. You've got 21.33 milliliters of 0.1199 molar NaOH reacting to reach the endpoint of a reaction with 25 milliliters of an unknown concentration of hydrochloric acid. What we want to know is, what is that concentration? We've given you a balanced chemical equation here already. You just got to figure out how to get to the concentration. And so I'll give you a couple of minutes and we'll talk about it, and that's where we'll end for the week. All right, so this one, because it's a titration, because ultimately we're looking at concentrations that we're interested in, we can use the titration equation for this particular one. So what we don't know the concentration of the acid, but we do know that we had 25 milliliters of it. We also know that our stoichiometry is all 1 to 1 to 1 to 1 here. So our denominators here are ones, which is actually going to make this really an easy calculation to do. On the base side, we know that the molarity is 0.1199 molar. We know that the volume was 21.33 milliliters. And so all that we have to do is divide each side by 25. The milliliters cancel out. So our molarity of our acid is 0.1199 times 21.33 divided by 25.00, and I get 0.1023 molar HCl as my concentration for the HCl. So this is actually very, very similar to most of the types of titrations in terms of what kinds of numbers that you can get, how quickly you can get them. This is a really useful equation for those purposes. All right. Any questions here before I set you loose for the weekend?
I don't have any.